In previous videos, we saw that crystals growing in porous materials can cause damage depending on the level of pore filling and the supersaturation. In this video, we discuss how dangerously high supersaturations may develop. From a thermodynamic point of view, a crystal exerting pressure is in a higher energy state than one growing freely. So, when possible, crystals will grow out of the porous material as efflorescence or inside of the material in large, unfilled pores. Alternatively, as explained in our video on capillary rise and salt damage, salts may accumulate in the pores as rising groundwater evaporates. As this happens and their concentration rises, the ions diffuse back towards the more dilute solution in the interior of the body. The relative rates of capillary rise, evaporation, and diffusion determine whether the solution becomes supersaturated. If crystals precipitate, the same factors determine whether the supersaturation remains high enough to produce damaging crystallization pressure. Another destructive situation can arise during the drying of porous bodies, even if all the pores are large. If a large pore is filled with salt and the drying front retreats into the liquid film between the crystal and the pore wall, then very high supersaturations can be reached because there is no escape paths for the salt. A similar but larger scale situation would be found in porous materials containing patches of solution that are isolated through small pore entries. In such cases, drying can cause the local salt concentrations to increase substantially, implying that stones with such inhomogeneous pore size distributions are at a higher risk of salt damage. This is schematically represented here, where in the highlighted region, the solution is isolated because it is surrounded by small pores that the liquid vapor meniscus cannot penetrate. As the relative humidity drops and the region dries, all its dissolved salt will precipitate locally. High supersaturations and salt damage may also be reached in materials with finer pores, such as cementitious materials. For this, we consider cylindrical pores containing crystals with hemispherical tips. The curvature of their tips is kappa tip equals 2 over Re minus delta, where Re is the pore entry radius and delta is the thickness of the liquid film between the crystal and the pore wall. Such crystal tips would be in equilibrium with a supersaturated solution such that the natural logarithm of the supersaturation at the tip is equal to 2 times gamma Cl Vc over RT times Re minus delta, where gamma Cl is the crystal liquid interfacial energy, Vc is the molar volume of the crystal, R is the universal gas constant, and T is the absolute temperature. The curvature on the sides of the crystal is that of a cylinder half as large as that of the sphere, so that kappa side is equal to 1 over Re minus delta. That surface would be in equilibrium with a solution of lower supersaturation, such that the logarithm of the supersaturation at the side would be equal to gamma Cl Vc over RT times Re minus delta. However, the solution in the film is more concentrated than that because it is enriched by diffusion from the bulk solution that is more concentrated as it must satisfy the higher solubility of the crystal tip. Therefore, there is a supersaturation in the liquid film so that the crystal sides have a drive to grow. However, they cannot do that because they are prevented from making contact with the pore wall because of surface forces, as explained in our video, Chemo-Poromechanics of salt damage. Under such conditions, it can be shown that a disjoining pressure is applied by the porous matrix to resist the crystal growth, and that its magnitude is then given by P equals RT over VC times the difference between the natural logarithms of the supersaturation at the tip and at the side. For our cylindrical pore, this simplifies to the following expression for the disjoining pressure: P equals RT over 2 VC times the natural logarithm of the supersaturation at the tip. This pressure can also be expressed in relation to the pore size of the connecting channels. Substituting our previous expression for the supersaturation at the tip, we get that P equals RT over 2 VC times 2 gamma CL VC over RT times RE minus delta, which simplifies to gamma CL over RE minus delta. Importantly, the macroscopic stress in the body does not require all the pores to be filled with salt, but that stress is proportional to the fraction of the porosity occupied by crystals exerting pressure. Another important situation leading to severe salt damage involves phase changes taking place through dissolution and precipitation, driven by changes in temperature and/or moisture. A notorious example is sodium sulfate, which is extremely damaging to building stone. It is used in laboratory accelerated testing by using cycles of impregnation in a sodium sulfate solution followed by drying. Mass loss starts after a limited number of cycles and is used as a measure of the susceptibility to salt damage. Damage develops during the wetting phase when the temperature is below 30 degrees Celsius. To understand this, we examine the solubility of the main sodium sulfate phases as well as a phase diagram of this salt with respect to temperature and relative humidity. The phase diagram shows that the solution is stable at high humidity, regardless of temperature. It also shows that anhydrous thenodite is the stable phase at all temperatures if the humidity is low enough. Below 32 degrees Celsius, sodium sulfate decahydrate, or mirabolite, is the stable phase over a higher range of humidity. If a thenodite crystal is subject to increasing humidity at a temperature above 32 degrees Celsius, it will dissolve when the humidity reaches the equilibrium line separating thenodite from the solution. If the temperature is below 32 degrees Celsius, the thenodite should convert to mirabolite when it crosses the equilibrium line between thenodite and mirabolite. However, if mirabolite fails to nucleate, thenodite will persist until it reaches the dashed line, which is the extension of the equilibrium of thenodite with a solution. When that discontinuous line is reached, thenodite will dissolve. The resulting solution lies in the field where mirabolite is the equilibrium phase, so it will eventually nucleate and grow with a high driving force. The solubility diagram shows, for example, that when thenodite reaches the dashed line at 22 degrees Celsius, it dissolves to produce a solution with a concentration of about 3.8 moles per kilo of water, so it is highly supersaturated with respect to the equilibrium phase mirabolite, of which the solubility at that temperature is only about 1.5 moles per kilo of water. In accelerated tests, the solution invades the pores by capillarity during the wetting phase. During drying, thenodite forms because the drying conditions are above 32 degrees Celsius. Upon subsequent wetting, thenodite is present in the pores and dissolves. In doing so, it attempts to reach its solubility. Below 32 degrees Celsius, that solubility is higher than that of mirabolite shown in this part of the curve. Therefore, the solution is highly supersaturated with respect to mirabolite because of the dissolving phenidite. Precipitation of mirabolite causes crystallization pressures that are increasingly large as temperature decreases, explaining why damage is more extensive when rewetting occurs at low temperatures. A final remark about sodium sulfate is that there is also a metastable heptahydrate phase that we have overlooked here for simplicity. In conclusion, if given the possibility, salts will try to grow in unrestrained conditions without exerting crystallization pressure. Transport limitations involving the pore size and pore size distribution of the porous host, as well as drying rates, play an important role in determining whether this can happen. When crystallization pressure develops, the risk of damage increases not only with that pressure, but also with the fraction of pores filled with restrained crystals. All those factors combine to explain why phase changes occurring through coupled reactions of dissolution and precipitation, as for sodium sulfate, can be very damaging.